Good morning, participants. Myself, Dr. K. Durga Sham Prasad, HOD Triply, Vignan Institute of Engineering for Women, and convener of this STC short-term course on advanced simulation tools for power electronics, electromagnetics, and power systems. I welcome you all for day 2 of this STC. The day 2 schedule.
Hello, I think we lost your audio.
Power Force software and design of three-phase DC to AC converter in Power Force software. Day 2 resource persons G. Vinay sir, Power Electronics Support Engineer, and N. Vishwanath Garu, Application Engineer. So I would like to hand over session to the Vinay sir. Vinay sir,
Okay. Hi, sir. Good morning. Good morning to everyone.
please hand over the session.
Yeah, sure. Thank you. So, yeah. So yesterday we have covered the buck converter designing, simulating in the PSIM software. So hope everyone got the results about the buck converter. So yeah, and another thing, we have given the boost converter simulation details also. Whether if any doubts you can ask about this boost converter simulation also. Hope everyone got fine. Okay. So now we can start with the simulating VSF in induction motor. So in PSIM software. So can you can see here. So here in the IGBT switches are used, and here.
Vinay, 1 second.
Yes.
One second, Vinay. So, have you shown the output of the boost converter for them?
Yeah, boost converter. Okay, I will show. Yeah.
Yeah, just show.
Vinay sir, your voice is very low.
Show them the output once.
Okay. My voice, sir. Hello.
Yeah, show them the output.
Yeah.
Everything was okay. Show them the output at once, and then you can start with the VSF detection.
Okay, fine, no problem. So, yeah.
And the presentation is also fine.
Okay, no problem. We will show once again in the boost converter what we have already simulated here. So this is the boost converter I have given yesterday as a to understand more. So where you can see the switching frequency is 20 kilohertz, and the input is 12 volt, and the output should be, we should get at 24 volt. And yeah, the duty ratio is 0.5 because we need to get 24 volt. So you can run the PSIM simulation where you can see here, everyone can see here the run option. So once if you click.
Sir,
Hello.
how did you select 0.5 duty cycle in that voltage source?
This actually be from the formula only I have selected.
No, from inside. Amplitude will be 0.5.
Okay.
Right.
Yes. Amplitude should be 0.5. That's it. Okay.
Because I tried it yesterday and I got a ramp waveform.
Oh, maybe because you have used some other source. This is actually pure DC source. Okay. So where you can see, you can find here on the screen, you can see the down itself. You can find this is pure DC film. And even you can use the constant block also to give that. Okay, because that is like okay. You can go further running. So here you can find VR is the voltage output voltage across the resistance. So here you can see this is the output voltage you are getting is 24 volt. Okay. So if you want to add another screen, so here everyone can see add one more screen. Okay. So just you can add and you can see the inductor current. So this is the inductor current. Everybody can see. So hope
Sir,
everyone
how to
got.
maximize the output wave?
Maximize means.
Sir, how to maximize the output waveform, sir?
Maximize means you want to increase the output voltage.
Shape, sir. Shape.
Okay, shape. You want to run more time. It means okay. Then you can increase this total time actually. But here, what is the problem? Demo version is having some limitations, right? So for that, we need to decrease the step time. Then we can increase the total time will be increased. Okay. So you can see. 1 minute. So now everybody can see. Okay. So here you can see. So we have run now 30 milliseconds because it was the step was like 10 to the power of -6, and also the print step is only 1. But now I have increased print step to 15. So that's why actually the waveform is getting more clarity. Okay, and you can run much time. Okay, so if you
Sir,
want to add, yeah, tell me.
how to increase the window size, sir? Window size.
Here it is
VR
there,
window.
VR window. So this one,
Yes, sir.
you can go for axis. I think in the axis variable. Okay.
They want to increase the font size.
Yeah.
If I'm
Font
correct.
size. Yes.
Yes, sir.
Yeah,
Yes,
they
sir.
want to increase. If they want to increase the font size, so just click on the options.
Okay.
Otherwise, here also it's fine. In the x-axis where you are seeing, no, there is a font option.
Yes. That's what I'm showing. So
So
here the
font
font.
option you can put increase.
Hmm.
So just click on the font.
Okay,
So there
okay.
you will have this
Dem.
shape and size of the font. So from that you can able to increase.
So the size you can see because
Not that one, sir. That is a rectangular box size.
this
See,
size.
here we are adding one more screen. Instead of that, you can able to
see one screen, and like if you are seeing one screen, then it will be window will be maximized window. Once if you can see here, if I'm adding only one element, then it will be fine. You can see now. Okay.
Okay, sir.
Now, but before I added another screen. Okay, if I'm adding here itself another waveform, then you can see here itself. See here, before it was in another window, but now in the same window. Okay, and you can there is a possibility like you can add for IL you can add another y-axis, so that you can see this y-axis is for output voltage, and this y-axis for inductor current. So that's
Sir,
tell me.
actually, I'm still getting that ramp waveform by doing everything. Means VDUT 0.5 and that triangular voltage, triangular waveform frequency 20 kilohertz, duty cycle 0.5.
Which point you are getting
check
that
the
ramp?
DC of the
Yeah,
triangular waveform.
Huh.
here.
Yeah. That portion.
So whether you
Comparator portion.
okay, so now you are keeping here voltmeter, right, to check,
Okay.
and now you run, and you can see now what is this point name. So V4 is the output of the reference. So here you can see the output of the reference is 0.5. Okay, this is a constant value.
Yeah.
Whether you are getting that value?
Means, no. Actually, I am getting VR voltage, output voltage, that will be ramp voltage, ramp waveform, not like a buck boost converter.
Okay, here itself you are
I'm
getting.
getting that waveform is a ramp. Yeah, I'm
Okay.
getting that ramp waveform.
So whether you have given
So what
every.
will?
Oh, wait. Whether you given the values are correct. So can you verify
Yeah,
once?
yeah,
The DC
exactly.
offset. DC offset. What about the DC offset?
Yeah.
Yeah, 0.5.
Hmm.
DC offset will be -1. I have given -1. Will be 0.
Yes, it will be 0.
Yeah.
Okay.
Because we are only sensing this is the positive.
Yeah. I got it, sir. So
Yeah.
means
Yeah.
DC offset. What is that significance of that DC offset? Means
See,
what will happen?
when you are using when you are for using the sine wave, when it is in the negative value
Yeah.
comes, then you can use for the offset value. Okay, it is like
Okay.
if you are using the DC offset, so the peak value if it is 2, means peak to peak is 2 means the positive value is 1 and the negative value will be 1. Okay.
-1.
Yeah,
Okay.
yeah, -1. Yeah, same like the sinusoidal representation it will come.
Yeah.
Okay.
Okay.
So
Thank you,
that's
sir.
what, yeah. If you have any thing like this, you can put the voltmeter and check whether if it is correct every point. So by checking back to
Oh,
back, you will get everything. Okay. Simply you will get out.
okay. Yeah.
Okay, fine. Mm. So any other queries on this?
So yes, Vinay. So we can start with VSF8.
Yes. Okay, fine. So now we are going to implement this one. We just show the PPT ones. Yeah. So now we are going to implement the VSF induction motor in PSIM. So where you can see it is having the 3 legs of IGBTs. Okay, and the DC source. Once we can create the power circuit, then we can go for the load. So for creating the power circuit, we need the IGBTs of 3 legs. Okay. So you can open, you can click here in the blank, create new document in the PSIM software, and this white space you will get. Okay, so you can close this if you want. Yeah. So white space you will get. Now we can go for the IGBT. So everybody can open the elements in the top. You can find the elements. So in the elements you can see the power.
So 1 second, Vinay.
Yes.
So if someone is not facing this kind of tab window, so you can go to view, view option.
Yeah, library browser will be
Application
there.
log.
Yeah.
No, application log. Go to application log, the first one, and then keep select here tabbed. So then all the applications will be open in the 1 by 1 page. So instead of opening in the separate pages, it will be in one window. So you can select this. And if you want to see the dotted lines, go to options, click on the options window, and go to settings, options and settings, click on the settings, and here display grid. So the first one is the display grid. Click on display grid. So this will be very easy for you in order to draw the lines. So if you didn't have this option, just go to options and then settings and display grid. So you can take this part.
Yes. This part. Okay. So
Based upon your convenience, you can be able to work out.
Yes.
So yes, Vinay, continue.
Yeah. Hope everyone open PSIM software, and here you can see create new document. Once if you create new document, the white blank space will be open with untitled. Okay. So The next, we need to find our elements. Okay, we need to go for the IGBTs, first one, or DC source. So the DC source you can find in the elements. Okay, sources and voltage and DC. So hope everyone can see the screen. So you will get elements, sources, voltage. In the voltage folder, you will get the DC. DC is the DC voltage source. Okay, just click on the DC. So you will get voltage source. I'm showing you again. Just go to the power and go to the elements, and next in the elements you can find the sources. In the sources you can find the voltage. In the voltage you can find the DC. That is called DC voltage source. You can click on there, DC voltage source, and keep on the plane. Okay. So the next one, go to the elements. Go to the elements, and next go to the power. It is the first option only. Then go to the switches. Okay. In the power, you can find the switches operation. So in the switches option, you can find the IGBT. You can see my screen. If you have any doubt, you can get IGBT and just click on the IGBT and keep on the screen. We need 3 legs. Okay, every leg is containing 2 IGBTs. So just place IGBTs. So after placing, you can press exit button to leave the cursor. So I'm showing you again where to get IGBT. Just go to the elements, and next one is the power, and in the power option you can find the switches. In the switches you can get the IGBT. Okay, so click on the IGBT and keep wherever in the plane. So make 3 legs. Okay. And after that, you can see in the screen, you can tilt the wire to connect all the elements. You can connect with the wire. So yeah, if any doubts, you can ask. Okay, I'm showing the circuit diagram once again in the PPT. You can just take a snap, or as you can see. So here contain the 3 sets of IGBTs with the DC voltage source. This is the power circuit, and after that, ammeters, 3 ammeters. Next one is the induction motor, speed sensor, and load. It's a constant torque load. Okay, so this is the power diagram. First we will complete the power circuit, then we'll go to the control circuit. Okay. So after keeping IGBTs and DC voltage source, just connect all these things. This way you can connect. Okay. once you can, after connecting, you can press exit button to leave the cursor from wire. Okay. So hope everyone connected. So the DC source you can find in the sources. Okay, in the elements you can find the sources and voltage and DC. So DC is the DC voltage source. You can keep. And the next one is we need to keep the ammeters to see output current from this inverter. Okay. For that we need to go for the elements, or we can find here itself. So everybody can see down there is a library ammeter you can get. Everybody can see ammeter on the screen. Downside. So you can connect here 3 ammeters. You can place 3 ammeters. Once you place the ammeters, then next one is induction motor. So everybody got ammeter, right? So here in the downside you can see ammeter. Okay. So after that you can connect with the wire. You can get the wire from here. Just connect the first one with the first leg, and second one with the second leg, and third one with the third leg. Okay. So next one is induction motor we need to keep. So for the induction motor, go to the elements first. And the elements, you can find the first option is power. So you can go to the power option, and in that motor drive module. So everybody can see here motor drive module. So first elements, first you go to the elements, then after power option. In the power you can see the motor drive module. In the motor drive module you can find all the motors. Okay, where you can see this all the motors. So first go to the elements, power, then after motor drive module, then squirrel cage induction motor. The first one itself you can take. Okay. So you can place here. I'm showing you again how to where to take motor. Just go to the elements, then after go to the power, then after motor drive module. In that you can find the squirrel cage induction machine. Okay. So you can take the squirrel cage induction. Just click on the motor, the squirrel cage induction motor. Place wherever you want. Just click, single click, and after that press the exit button to leave the cursor. Okay. So until induction motor we completed. Now we need the speed sensor to see the induction motor speed. Okay. For that we need to go elements, same library. So in the elements you can see the power option, first option, and in that mechanical load sensors. So this will be there, mechanical load sensors. Okay. So I'm just displaying on the screen. You can find mechanical load sensors in power option. In that speed sensor, from the last, it is the second one, speed sensor. Okay. Just click on that and you will get the speed sensor. Place beside the induction motor, and after press exit. So this speed sensor, basically it is a initial. Normally it will give in the RPM only, the output speed. So there is no need of keeping another gain to see speed and all. So the next we have completed induction motor, speed, sensor. Now we need to keep the load. Okay. So for the load, again we need to go elements, power option. In the power you can find the mechanical loads and sensors. Okay. In that you can take the mechanical load, you can take the constant torque. Okay. So everybody can see in the elements power option. In the power you can go for the mechanical loads and sensors. In the mechanical loads and sensors you will get the mechanical load. It is a constant mechanical load. So just click on the constant mechanical load, constant torque. Okay, you will get this and place beside the speed sensor. And press exit to leave the cursor. So now you can take the wire option and connect this all ammeter, second ammeter to the second terminal, and the third ammeter to third terminal, first ammeter to first terminal. So we have connected ammeters to the induction motor. Okay. From the induction motor shaft, we are connecting to a speed sensor. Okay. And the speed sensor is connected to the load. So yeah, now we have completed the power circuit. Okay. So we have connected a DC voltage source, IGBTs, and ammeters. Then after induction machine, and speed sensor, and the next one is the load. Mechanical load. It is a constant torque mechanical load. Okay. Here you can see the torque symbol T. Okay. Now, so till the power circuit we have completed. Now we just want to go to control circuit. Okay. So where here we are using the sine PWM. Okay, sine PWM with a triangular waveform. So we are comparing and pulses. We are generating the pulses. Okay, that is why we are going to generate the gate signals. So first we have to take here a three-phase sine waveform, three-phase sine source. So in the elements, you can go to the elements. Okay, in the elements you can go to the sources. In the sources you can go to the voltage source means. Okay, in that you can find the three-phase sine. So I'm just displaying on the screen. If you any doubt, you can see elements. From the elements you can see the sources. From the sources you can go to the voltage. From the voltage you can select the three-phase sine. Okay, so just click on the three-phase sine waveform, sorry, voltage source. So you will get this. Place little distance from here, and after that press exit. If your screen is like you want to just fit whatever the elements are there in your screen, if you want to fit to see proper, then you can go for the zoom to fit page. Okay, option is there, zoom to fit page. So it will automatically fit all the elements to the page size. This is zoom out to if you want to see more clarity, and if you want to find all the elements in the single view, then you can use this. So now we got three-phase sine voltage. I'm showing you again. You can go to the elements. In the elements, you can find the sources. In the sources, you can see the voltage. In the voltage, you can find the three-phase sine. Okay. Okay. So after that, now we need to take the comparators. Okay, to compare the signals. So yeah. In the bottom, you can find the comparator. I'm just placing my cursor so everybody can see comparator. So where you can get comparator, I'm just showing. So you can place 3 comparators. Just place the 3 comparators to compare. Okay. Now take the wire up. Now you can take the ground also. You can ground you can see on the screen. I'm showing you left side bottom. You can find the ground. Just keep on ground here for the power circuit, and for this sign source, 3-phase source, you can keep the ground. So we have kept 2 grounds. Now press exit to leave the cursor. Now go to the wire and connect sine wave sine source to positive terminal of the comparators. Okay, you can connect all the signs, each sine source to positive terminal of the comparator. You can connect. Okay. Hope everyone connecting. If you have any doubts, you can ask. So we have connected sine wave 3-phase sine signal to comparators. Okay. So next one, we have the sine source now, but that sine signal we need to compare with the triangular waveform. So for that we need to keep triangular source also. Okay. So you can get the elements, sources, voltage. So you can get from here triangular. I'm just displaying my screen. You can see. So elements, sources, voltage. In the voltage you can find the triangular. So this is a triangular voltage source. Just click on that triangular voltage source and keep here and press exit. Now you can take the ground to connect this. Just in the bottom side you connect the ground and press exit. Then take the wire option to connect all the negative terminal of the comparators. Connect all the negative terminals. When you're connecting, be cautious because these wires may get short. Okay, so if it is get short, the black dot will form. So this should be short to this line, so that is not a problem. But this sine source should not be shorter to this source. Okay, so that is please take care. You should not get intersect each other. Okay, now in the PSIM. Okay. Now in the PSIM, actually for triggering any IGBT or MOSFET, you need to use the one on and off switch controller. Okay. Just it is like great driver circuit for this IGBT. We can tell that like that. So this on and off switch control is required. Okay. For every switch, we need to keep this on and off. Okay, controller. So for that, we need to keep this 2 sets for every switch. We need to keep one on and off controller. So just you can place here. So for upper switch and the bottom switch, both switch, 2 on and off controller for every leg. After that, press exit to leave the cursor. Now, yeah, so can everybody find here, right? On and off switch controller in the bottom. In the bottom library itself, you can get beside the gating block. It is there. Okay. Beside the gating block, on and off control switch controller. This is actually needed for every switch. One on and off gate controller is required. For that only, for every MOSFET, I kept one each one. So overall, 6 MOSFETs, sorry, 6 IGBTs. So for that, we have kept 6 on and off control switches. So here in the inverter, we know another thing is in every leg. In every leg, another the IGBTs are complement to each other. Okay, when it is when we so that for that we need to use NOT gate to give different complement voltage getting signals. Okay, so we need to give NOT gate to give the complement signals to in every leg. Okay, so for that, go to the elements. After that, control, and after that, logic elements. In that NOT gate, you can find. You can see my screen. Just I placed control in elements. You can find the control block, control module. There, logic elements. In the logic elements, you can find the NOT gate. Just click on the NOT gate, and you will get this. And for rotating this, you can click your right soft key in your mouse. Just place for every leg we need one NOT gate to give the complement getting signal. Okay, so we have now we can go for the connection. So just take the wire, and first you can connect this every on and off switch controller. You can connect to the one IGBT. So be cautious while this connection, because the output terminal should not get short to this gate. Okay. Now, yeah, we have completed till this part. Now,
Sir, once tell me complement diode rates.
which one, ma'am? Hello. Yeah. Okay. Fine. See here, in the every leg, the gating signal should be complement to another switch. Okay. So if it is a positive here, it should be negative here. So that is why we are actually using the NOT gate in every switch. Okay. So the NOT gate we need to connect to every switch. Sorry, one switch to every in every leg module. So in the leg, I'm connecting this to only one switch. Okay. So I'm connecting to only one switch. The bottom switch I'm connecting. Now you can connect these two.
Sir,
Yes, yes.
in MATLAB, we are giving a duty cycle to the each MOSFET or IGBT, right?
Yes.
So here we are not giving any duty cycle, means for 60 degree, next is a 180 degree, another is.
Actually, that 60 degree, 180 degree and all, that is phase controller. So when you are using for the phase regulators, means voltage regulators and all, you have to give the duty ratio. Okay.
Okay.
Here we are doing inverter operation. So inverter operation doesn't require that actually. So you need to give the references sine signal. So maybe it is sine PWM or else SUPWM, state vector PWM.
Okay.
So like
Okay.
that. Yeah.
Means we are using PWM techniques, right?
Yes, yes, they're actually different. That is regulating voltage regulating. Okay, so to cut the
Okay.
output voltage, so that we are using that duty ratio there, means angle, firing angle. Okay, so everybody can connect like this. If you have any doubts, you can ask.
Sir, once tell me where is the complement diode?
Complement diode. So sorry, actually this is not complement diode. This is actually not gate. Okay, where everyone can find in elements. First you go to the elements, after control. Okay, in the control you can find the logic elements. In the logic elements you can find the not gate, not not. Okay, not gate you can find. So just click on that. You can see my screen once, then you will understand more. Okay, control. In the control you can find the logic elements. In the logic elements you will get the not gate. Okay. So this is what not gate. So for rotating not gate, you can use the your mouse right hand key. So yeah. So after everybody got all the elements right. If you have any doubts to take element, where to take elements, you can ask.
Sir, how to take speed sensor?
Okay, speed sensor. First go to the elements. Okay, and how to go first to go to the elements and the power next to the power. Okay, the first option is power. In the power you will get the mechanical loads and sensors. Okay, in the mechanical loads and sensor you can see the down speed sensor. In the same folder you can get the torque, mechanical load torque also. Okay, speed sensor and mechanical load torque, both you will get here. You can see the screen. And another thing here, the color, everybody seeing this color difference, right? So in this actually red color and here is a green color. So the red color, it defines the it is a power circuit. Okay, so we can't change that actually color. So this is it defines the power circuit, and the green color will defines the control circuit. Okay.
So if they want to change the color, they have to go to options and then they could change these colors.
Okay.
But by default, for easy representation, the red color will be the power circuit and green color will be the control circuit and blue color all the elements.
Yes.
So if you want to change that, you have to go to the options and you can change the colors of the elements. And regarding the ammeters, you will find it in the probes part, or otherwise in the down commonly used blocks, you can able to find it.
Yes. Or else you can go to the elements. In elements others, okay, in other you can find the probes. So here you can see, yeah.
So regarding the colors, you can able to show them, Vinay, once go to options.
Yes. Yeah. Okay.
Settings. And then this particular colors. After advanced, you have a colors. So
Yes.
these are by default, these are the colors which will get it. So these the grid color, elements color, subcircuits. So white colors. So if you want to change some some color part, you can able to right click on the dotted lines and you can able to change.
This. But anyhow, if we change also, the differentiator will be same. Okay. Yeah. So yeah, so we have built the circuit. So I hope everyone completed circuit, right? So now you can take this voltage probe. So that probe you can keep to see the speed at speed sensor. Okay, here on the speed sensor you can keep voltage probe. Here on the down part in the common used blocks you can get voltage probe. That voltage probe you can keep at a speed sensor by rotating. Okay. Okay, nice. So the next we have now we'll go to the parameter setting now. Okay, so the input everybody can define 500 volt. Okay, and you can click here to display the
Sir,
input
once
of
again say voltage sensor.
voltage sensor. So this is the voltage probe. Okay, it is not voltage sensor. Sensor is different. So here in the downside you can commonly use blocks are there right down. So there you can get the voltage probe. Okay, node to ground probe you can take and take that probe, but initially the direction is different. So you can rotate. You can use your mouse right key to rotate it and just place here. Okay.
Sir, how to change the color of circuit, sir?
You can go to the options first. In options you can find the settings. In the settings you can go for the colors option is there. So there you can find the elements color and sub-circuit color. So here you can change.
Okay, okay, sir.
But you can't change the particular circuit, but you can change all the circuits. Okay.
Okay, sir.
So the next one, please provide the input for the DC voltage source input. You can give the 500 voltage as amplitude and just close. No need of saving. When you close itself, it will automatically you will get saved. Okay. So the next one is torque. So this is like load. We can change the name if you want, and you can provide 40 is the torque, and yeah. Okay. Open the load, mechanical load, and keep the constant torque as a 40. And if you have any doubts, you can go for the help option also. If you open the help option, so here you can see the units of the torque, means Newton meter, that, and how the torque is calculating that, everything information they will provide. Okay, in the help option. And also here in this you can see where the elements is in the library, PSIM library, where it the element. So mechanical load, this is the torque is mechanical torque is there, like that you can see. Okay, and after that just close it, will automatically get saved. So the power circuit, don't change any parameters.
Sir, what is?
Yes. Hello.
Sir, comparator negative terminal connected signal. What is that signal?
This is actually triangular waveform, sir. Triangular waveform to compare the sinusoidal waveform.
Okay.
Yes.
Fine, sir.
Okay, fine.
Thank you.
So don't change any parameters of the induction motor. Whatever we here we are doing, that is default for this induction motor only. So no need of changing any induction motor parameters. But if you want to see the parameters, just open and you can see. Okay. And if you want to know further about the parameters and all, you can go for the help option. So there you can find what are the units and what is the parameters. Everything you can see. Okay. So we have changed only two parameters. Voltage, DC voltage source is the 500 volt, and load torque, yeah, 400. Tell me.
Sir, how name will be displayed on element, sir? Near element.
Yeah.
We have.
See, in the elements you can see when you open this any element, you can find the display option. Okay. in the display option, you can make it as a mark. So once if you make
Okay,
it
sir.
mark, so it will display in the screen.
Okay. Thank you.
Okay, thank you. So next, so we have completed the power circuit part. Now we have to go for the control circuit. So hope everyone connected everything right. Hope applied the voltage and the torque. So the next one is
They're applying the voltage on this.
sorry, can you please tell me?
Voltage, applying voltage.
Yes. You can just click on the voltage source. Whatever we have kept voltage source here, right? Just click on the voltage source and apply the amplitude as the 500. Okay. Apply the amplitude as a 500. After that, close and open the mechanical load and apply the constant torque as a 40 and just close. Okay. Now we can go for the this signal part, means getting part. So we can open this three-phase sine. Yeah, we are recording the session, so we can send you after the session. So in this, you can provide the voltage. V line voltage is 0.9. Okay, and the frequency, if you want change, you can change to 50 hertz. So 0.9 and 50 hertz. Okay. So I'm showing you again. The sine voltage is a 0.9 voltage and the frequency is 50 hertz. Everybody can apply 0.9 voltage and 50 hertz. Okay. Yeah, fine. Next one is the triangular voltage. To compare, so everybody can open the triangular voltage source. So the V peak to peak is 2 volt. Okay, it is default as a 2 volt. Don't need to change. And the switching frequency. This is actually frequency. We can think like it's switching frequency. So we can provide 1500. Okay, switching frequency. And the duty cycle is 0.5. And the DC offset is -1. So hope everyone can see screen. Yeah, displaying. Okay, I'm showing again. Just you need to change here the switching frequency is 1500. Okay, it is default as 1000, but you need to change to 1500.
Sir,
Yeah.
in this triangular waveform, we are putting DC offset -1.
Yes, because here you can see we are actually going to sample the compare with the sine
waveform.
Yeah, the sine will be like
Okay.
negative.
Whenever there is a sine waveform,
Yeah.
the DC offset will be -1.
Yeah, we can say like that, but this is not for all cases, okay? Because we need to get a triangular waveform in the negative point of view, negative also. At the same time, how much we are getting the positive, like that only we should get negative also to compare the signal of sine. Okay, so for that we are using this here. Okay.
Yeah. Okay.
It is actually here you can see the peak value, peak to peak is 2 volt, right? So it means the positive peak to negative peak, it is 2 volt. Okay, it doesn't mean that maximum value is 2. Okay.
1 to -1 volt, right?
Yeah, 1 to -1. How much is difference is 2 volt, right? That's what actually it means.
2 volt. Yeah.
Peak
Exactly.
to peak. Yeah, and because the DC offset is -1, so for that only the -1 +1 value is the positive, -1 is the negative value. That will.
Okay, okay.
Fine. So after you can close.
So once repeat the three-phase voltage source values.
Yes, yes. So in the three-phase voltage source, you need to change the frequency. Okay, whatever you want to get output frequency, that you can change.
Sir, if we take V peak equal to 1,
Okay.
then we need to take D offset equal to -0.5, sir.
Which which one you are saying?
If we take V peak, yes,
Yeah.
sir.
Okay.
If we take V peak equal to 1, then we
Okay.
need to take DC offset as -0.5, sir.
Yeah, it is like see, if you are taking V peak, peak to peak is 1 means if you have to take DC offset value is a 0.5, okay, -0.5.
Yeah, okay.
But at the same time, your sign voltage also should be less than 0.5.
Okay.
Okay, because it should compare, right?
Okay.
So far that
Line to line, yes, sir.
yes, this should be less
Yeah.
than whatever you are giving the sampling voltage. Okay.
It should be less than carrier frequency.
Yes, yes. Fine.
Carrier amplitude. Yeah.
Yes, yes. Correct. Carrier. Yeah.
Yeah. So this is a under modulation technique, right? It means.
Yes, yes. So next one, you can go for the simulate option. So we have given all the parameters. Now you can go for the simulate option, and first option you can select simulation control.
So please wait a minute.
Yeah, yeah, sure.
So once can you say about the induction motor and the load connection once again?
Yes, yes. So the induction motor, I'm saying that default whatever the values are there, just you keep that values, okay? Because we are going to do only the basic understanding, so we are not doing any analysis, right? So for that you don't need to change any values. Just keep whatever the induction motor you had took from the library, and you have to connect that output terminal to the speed sensor, and the speed sensor should connect it with the load, okay? The load value
It
is
should be connected to the speed sensor, right?
yes, yes, it should be connected to the speed sensor.
So once again, can you say where we can get the speed sensor element?
Yes, yes. In the elements, okay, if you go to the elements, the first option called power, you go to the power option. In the power, sorry. In the power, you can see the mechanical loads and sensors. In there, the last second option is called the speed sensor. Okay.
Okay, sir. Thank you very much.
Yeah, yeah. Welcome. So yeah. So the next one is yes, yes. We will share the PPT also. So next one, you can open the simulation control. You will get this. You can go to the simulate option, and in the simulate option, you can find the first one, simulation control. Just click on there, and you will get the clock symbol and place on the screen. Okay, yeah.
Hello, sir.
Yes, yes. Tell me, sir.
Sir, before just simulating, please let me briefly explain the operation which you are going to show it.
Yes, yes. Sure, sure. I will show.
Before simulating.
Yes, yes. So yeah, now what happening is here we are actually making inverter operation by using the sine PW. Okay, so here we will get the sine voltage as the output voltage. Okay, when if it is a so the switches or we are given the here we can see this sine wave. What it will generate is it will generate the three waveforms. One is like a 120 degrees phase shift apart. Okay, so each so every switch will be operated the 120 degrees apart. So finally we will get the three phase output here. So I can show that output, three-phase output. But before that, yeah, and another thing, because we are using the IGBTs, we don't need to go for the high. We should not go for the high switching frequencies like how we are used for the MOSFET. Because if we go to the high switching frequency, the MOSFET because it is a high IGBT is having the more higher current handling capability. So for the if you are using for the high switching frequency, there will be loss, huge loss. So for that, you should not. And also, IGBTs are designed for the low switching frequencies only. Okay, for high current range. So that's why we are using only 1500 as a frequency. Yeah, switching frequency. Okay. So now go to the simulation control. Okay. The simulation control. Here you can see the time step. Okay, first one is the time step, and next one is the total time. So total time you can change it till 0.4 seconds, and print step also you can change to 15, and time step you can just leave like about 10 to the power of -5. So everybody can see the screen, right? So I'm just showing the time step is 10 to the power of -5, and the total time is 0.4 second, and print step is 15. Because actually in this demo version having some limitations, so we can't run much time. So that is the reason I'm just here, and after that close. Okay, then now you can go for the run. Okay, run PSIM simulation. So it will answer the one, then you can. Now we can see here we got the 3 currents and 1 voltage. This voltage is the speed. So we can do one thing.
Sir, where is the run option, sir?
Which one?
Where, how could we run the application, sir?
Yes,
where
yes.
we have to click on the
So
run.
did you place this simulation control?
Okay, sir. Is it over, sir? Up to
Okay,
simulation
fine.
link is over.
Yes,
So
yes.
afterwards.
Run the PSIM simulation. Can you see on the screen?
Yes.
You can see on the screen, or else you can go to the simulate option.
Run
Yes,
sim
yes.
view, sir. Is it run sim view?
No.
Okay.
Run sim view is actually after the simulation running for seeing the results. Okay. You can see in the
Okay, sir.
screen. In the screen, you can see first simulate. You go to the simulate option. There you can find the run
Okay.
simulation. Run simulation.
Okay. Okay. In simulation option, run simulation.
Yes, yes.
Okay, sir. I have to click on the run simulation.
Yes, yes, correct. So now you can select the outputs after the simulation complete. Hello?
The current probe is floating. It is showing the error, sir.
Which one? Current probe is floating.
Yes, sir.
I think you didn't connect current probe properly. Just check the verify connection once. The current ammeter probes.
Sir, I got a one error.
Okay, which one?
The printing starting time is larger than the total time.
Okay, how much time you
Change
have?
the printing.
How much time you have entered in step time?
Step
Print
time.
step as 1 and stand step as 6.6 e power 005 and the total time as 0.4. It will run.
Okay.
005. Yeah.
Wait, 6.66 e power of minus. Okay.
5.
Okay. 0.4.
Yes, this will work out. Or you can keep 3.35 also, not a problem, because it is.
Yeah. 1 minute. Yeah. So everybody can open the simulation control block once, and please enter these values. Time step is 6.66 e power of -5. Please enter these values.
So in this you can find the variable time step also. So variable time step solvers are easy to use. Basically the sampling time is automatically determined. In some cases what you have to do is in the particularly real-time applications, they did not have the prior next step value. So in that case, what they will do, they will go for the variable time step. So for smaller sample time or the bigger sample time, so they will work on that either in the hardware in loop or in processor in loop. As they don't know the time step, they will use the variable time step. So accordingly, it will divide whatever the time step you have given. Accordingly, it will divide with the multiples of 4 or 6. So in that you can able to see. So accordingly, it will divide and you will get the output, proper output.
Yes, yes. Time step ratios. Yeah.
And so one important aspect of time step selection should always be based upon your frequency component. What is the highest frequency component? You have to select according to that. So typical suggestion will be the time step into your frequency should be less than or equal to 5 to 10%. So that will be around 25 to 50 microsecond for a transient of, for example, if I have a 2 kHz frequency, so we can able to take 25 to 50 microseconds. And for switching power converters like voltage source converters, so time step should be as small as possible. That should be 0.2 to 1% per 1 kHz.
Yes.
Hello.
Yes.
Hello. Sir, I'm getting the error, sir.
What is
in
that?
element IP name I1 means ammeter, sir. First ammeter I am getting the error, sir. The error is the current probe I1 is floating.
Oh,
floating means that it is not connected properly. Somewhere it is open. Oh, it become open. So floating is nothing but it became open. So it is not connected to the circuit.
Just check the connection, the ammeter connection once again, and you will get.
Okay.
So yeah. So everybody.
So you can do one thing, just place one more ammeter and show that error. So just place here.
Yeah. So example, I can show like this, right? Just I will keep see. Everybody can see. I'm not connecting this ammeter fully. So if it is the black dot comes only, it is connected. If it does not come, it didn't mean that it is connected. So if you run simulation now, so you will get a see the current probe I1 is floating. Okay, because the it is not connected to the line. So
okay, sir.
Yeah, you check once again and then you can connect, or else you can delete that connection once again and you will do that again. Then it will be nice.
Yes, you can give the gating blocks also like yesterday, but only problem you should give the correct gating signals. So the firing angle should be as proper. You should maintain properly. So then only the circuit will work.
Hello.
Hello, sir. Yes, yes.
Sir, in simulation, what is the print step value?
Time step. Okay.
You can take one.
One you can take. Yeah.
Okay.
I'm showing on the screen. You can see.
Hello, sir.
Yes.
Hello. Hello.
Yes, yes.
Sir, how to calculate TH3 for each and every waveform, sir?
Yeah, in the SIMU window, you open the SIMU window, means the output results window. So there you can find I1, I2, I3. So you can add to the variable for the display, and after showing this, okay, you can go for the analysis. In the analysis part, you can find the THD. So for the THD, you need to give the fundamental frequency. Okay, 50 Hz is the fundamental frequency, and here you got the THD. Okay, for every waveform.
Thank you, sir.
I1, I2, I3. Okay.
Okay, thank you, sir.
Okay, fine.
Hello.
Yes, yes.
Hello.
Tell me, sir.
This is Sharath.
Yeah, tell me, sir.
Hello.
Yes, sir. Tell me.
Hello. Is it audible?
Yeah, you
Yes,
are audible.
we can.
You are audible.
So my query is, so in MATLAB usually we can store the data for each and every sampling instant. So is there any chance in this PSIM software you can stack like that?
Yes,
Storing
yes.
the data so that you can save the
Say
flag.
once we can we get the data? Suppose
You want
once
to get
we
in?
got the simulation, Excel sheet or some
Yes.
data.
Yes, that is possible. So when I just
it
open the CPU once and right click on this, view data points.
Data points. Yeah.
View data points. First.
So here you can see.
So here you get with each and every sampling time you get each data points. So this you can copy into Excel.
Yeah. Thank you very much. Thank you.
Yeah, you're welcome.
Yes, we can able to create the lookup table. It is possible. So we have a direct lookup table also. It is possible.
So yeah, so everybody can run the simulation by using the simulate option. Run, simulate and run simulation. And next, here you can select the speed and you can add the variable display and just you can see the speed. Because here we are getting the speed required speed, but because we are not here the problem it is the initial stage, so it will reach some time like a 0.4 seconds to reach the final speed.
Sir, can you show me the exact waveforms once to check whether I'm getting clearly or not?
Yeah, I'm showing
After
I'm showing the current output values. Okay, you can see. So this is what in the initial stage.
Yes, we'll show you the end of the session, maybe with smart control and then the MATLAB interface. I will show you that.
So here you can see the starting it will induction motor requires the large current, right? So that is what happening here. And after it comes to the near to the rated speed, the current value is decreasing. Here you can see.
I'm not getting that waveform, so that's why I'm asking.
I think here
Sir,
what you're getting, I know.
they are getting waveform along with the speed, sir.
Actually, once when you are open the SimView window, just close the SimView window and once again click on the SimView window. So in the SimView window, you just select the variables I1, I2, and I3. Only these three variables you select, and after that you add. Okay, there is a option called add, and just click OK. Then you will get only the current waveforms.
Okay, sir.
After that, if you want to see the speed, you can add one more screen. Here you can see add one screen. So there you can select only speed and add and click OK. Then you will get two waveforms separately. Okay.
Sir, waveform like constant DC I'm getting, sir, even though I'm selecting I1, I2, I3.
Okay.
I'm not getting the variable values of I1, I2, I3. Constant DC.
Okay. Okay. How much time actually? Time means x-axis. How much time it is coming?
I will check it.
Yeah. You check the waveform. How much time it is running?
After selecting I1, I2, I3, I have to click on the add.
Yeah.
There afterward, I'm going to click on
OK.
OK.
Yeah.
I'm not getting, sir.
How much time?
At zero axis only, I'm getting it directed like DC output. I'm getting at zero only. I'm getting that.
Sir, the time period is 0.4, sir. is coming from 0 to 0.4, a single line of 0, sir.
Oh.
Yes, sir. I am also getting the same.
I2, I1,
Single
I2,
line.
I3.
Not getting.
Before displaying this, it is saying that you have given a time of 6,000 seconds, something error is coming, sir.
That is
Warning,
It is
the
not an error,
maximum
that is a warning.
data
That's
points
not an error.
for the
Yeah.
version
See,
is
please.
6,000 data.
Okay. Please.
So one by one,
from
and
0
let
to
me clear all the doubts. Vinay, so you have understood what they're asking.
So please, everyone check.
0 to 0. Same 0 from 0 to 0.4 seconds. 0 value getting, sir. That is only the output.
Sir, our x-axis is only displayed from 0 to 1, sir.
Mine is displaying 0 to 0.4.
Okay.
X-axis, sorry, y-axis is from -1 to 1, sir. Y-axis.
Okay. I just want to clear that you some inputs I think you might have given wrong. Okay. Just
Minus 400 to 400.
see. Okay, fine. I'm just giving. You can see here my screen. Follow the all the inputs once again and verify, and we can.
Yes.
Yeah. First, the input is 500. Input voltage.
Yes, sir.
Yes, sir. 500, sir.
Okay.
EDC 500, sir.
Yeah. The next
500
one.
amp.
Yeah. Next one, load is 40. Okay. Constant torque is the 40.
Yes, sir. Load 40.
Okay. Now go to the three-phase sine. Okay. In the line to line RMS is 0.9.
Okay.
Yes, sir.
0.9. Okay.
Frequency is 50.
50. Okay, sir. Frequency.
Remaining all the blocks are 0. Okay. In the remaining all the zeros only. Okay.
All the other remaining zeros.
Now open the triangular waveform.
Yes, sir.
So in this, V peak to peak is 2.
Yes, sir.
Okay. Frequency is 15.
We peak to peak to 2. Okay. Okay.
Yeah.
15.
Frequency
Okay.
is 1500.
Okay. Frequency 1500. Okay, sir.
Duty cycle is 0.5.
Okay, sir. 0.5 duty cycle.
Okay. DC offset is -1.
Yes, sir. Offset -1 DC offset.
Okay. And remaining 2 are zeros. Okay.
Okay, sir. Remaining 2 zeros.
So now you can run the simulation once. After running simulation, whether one window will open, right? It will give one.
Okay.
You just click OK.
Okay.
Then the properties window will open. In that, select I1, I2, I3.
Okay. I'm selection. Okay.
After that, add. There is an option called add beside that.
Okay.
Then
I'm add.
click OK.
Sir, how can I get speed in the properties window, sir?
Yes, I will tell. So whether you are getting now sine waveform?
No, sir. Again, same thing, sir.
So
from 0 to 0.4.
Not getting.
Wait. Whether you are connected this load properly to the induction motor?
Yes, sir.
Just check it once the connection to the load, because actually if the load is not connected, also some problem will come. And whether
the load is properly connected.
Okay, and these groundings are given properly, right?
Yes, sir.
Yeah, tell me. Can you see? Open the simulation control.
Okay, sir. I'm out.
Okay. Yeah. So
6.66 E.
Yeah,
6.66 E minus 0.005.
0.5. Yeah.
6.66 into 10. Okay.
Total time is
0.4.
0.4.
Okay, sir.
Print time is 0.
Okay.
Print step is 1.
Print step 1.
Yeah.
Okay.
Sir, I think they need to click gates and diodes.
Okay. Maybe I think you are instead of on and off control switch, are you using diode? Whether
they are connected. I think diode there.
Please Yeah, please change this. This is on and off control switch. Okay, and just okay. Please see my screen once again.
Okay.
See my screen.
Okay, ma'am.
So this is on and off control switch. This is not diode. Okay. So this actually you can find in here. Inside the gating block, there is on and off control switch. Can you see?
Yes, sir.
Okay, on off switch controller, sir. On off switch
Yeah.
controller.
Yes. This is not diode.
I'm taking that. Yes, sir.
Okay.
Sir,
I'm taking that.
Okay. Next one, whether you're using not control, not gate.
Yes, sir. Not.
Yes, sir.
Sir,
Not yet. I'm getting not yet.
Yeah. And the connections are
Okay.
given properly. Just check once, because actually this.
Sir, we are properly given, sir. I'm properly given.
Okay.
Hello.
Yeah.
Hello, sir.
Yes.
Sir, what was it?
Sir, how can we get speed, sir?
Speed. Yeah. See, because we have kept for the speed sensor, we have kept 1 voltmeter, right?
Yeah.
So when you open the SIMU window, okay, then click that speed, means whatever the name you have kept here, you just answer the voltmeter's name. Okay, the voltmeter name you can see here. That name you need to remember. Then you open that in SIMU window. Okay, while selecting that voltmeter and add the screen, and you will get the speed.
Sir, can you say once again, sir?
Okay, we have connected one voltmeter to the speed controller, right?
Yeah.
So that name, what you have kept?
Speed.
Speed. Okay, fine. Then run the simulation. Okay. After running the simulation, can you see the speed option? Just click on the speed option and add.
Okay, sir.
Okay, and plus
Still V1 only, sir.
Huh?
Still now displaying V1 only.
V1? Okay.
Still now displaying V1 only, sir. I1, I2, I3, V1.
Okay.
Now I am not getting.
Whether you're
Getting only V1, sir.
Okay, V1.
I'm not getting speed, sir.
Hello.
Okay. The value.
Variable available.
Participants doubts after the session. Sir, please continue with session.
Okay, fine. So yeah, I think.
So what we'll do, we'll share this entire results to you. So the schematic files we'll share to you. You can able to work on that. So if any doubts is there, we'll share our mail IDs also. You can write us a mail. It will be very helpful. Okay. So hope everyone is fine with this thing. So what I will do, I'll just show you the advanced software compared to high-end analysis. Now we have done the basic analysis, so we'll see for some high-end analysis of the software. So let me take the control.
Yeah. Okay, fine.
Vinay, I'm taking the control, please.
Yeah, sure.
So, can everyone see my screen, right?
Yes, we can see.
Yes, sir.
Okay.
SIM control software, smart control software.
Smart control. So this software is called smart control. Basically, what will be the advantage of this software was to find the stability analysis. So as we know, we know about the frequency response. So in conventional control systems, there are two basic methods for predicting and adjusting a system performance. So those are called root locus and frequency response method. So for the comprehensive study of a system, the conventional methods, it is both necessary to use these basically and to get the stability response. So in this part, instead of root locus, I'm just explaining the frequency response where we'll have the Bode plots and the Nyquist plot. So basically, the frequency response is the steady state response of a system to a sinusoidal input. So hope everyone studied about the control systems. So just I'm giving the overview of the software. So and I'm just brushing up something for basic understanding what will be the Bode plot, what will be the Nyquist plot. So I'm just giving basic theory of that. So in the frequency response method, we vary the frequency of the input signal over a certain range and study the resulting response. So this is one of the basic understanding of the frequency response. So how we'll design that? The design of the feedback control system in industry is probably using the frequency response more often than any other way, primarily because it provides good designs compared to your root locus because of the phase of uncertainty in the plant model. So we have a different plant models like converter, boost converter, flyback or anything. So we have all the things available in the smart control, ready-made templates are available. So this is how the software looks like. So what exactly we have to do in the frequency response, the noise which is always present in the system, we should basically it will result in the poor performance. So we have to restrict that by giving the proper phase margin and gain margin according to that. So coming to the Nyquist stability, it enables one to investigate both the absolute and relative stabilities of linear closed loop systems for a knowledge of their open loop frequency response characteristics. So these are all methods which we have to take care in order to understand very well. So what about the smart control? Smart control is a control design software, especially for power electronic applications. It is very friendly to use, so simple workflow. So first you have to select your plant model and then the compensation model and then the sensor model. So once you selected all those things, we can able to design the proper, we can able to see the phase margin, gain margin, and then the Nyquist plot and then time response. So everything is available in the software. So starting from the specifications, we can able to design the control converters or the switch mode controllers or the inverters. So all this can be done with a easy method. So I'll show you the step-by-step procedure what we have to do. So we have the multi-loop control structures in the smart control. So in the right-hand side, you can see the plant model. So we have the different plant models which is readily available. So apart from that, we have the average current mode control and inner and outer loop compensations for the average peak current mode controls. So all these things are available in the smart control. So only thing you should be able to give the proper parameters while you are entering these values and with proper gain margin and the phase margin. So while you are changing these results, it will show you the real-time update for the waveforms for the Bode plot, Nyquist plot, and the time response, even with the inductor and current values. So all the data will be real-time updated. So this is the solution map. In this part, you can able to see. Let me take my pointer over here. So here you can see this is my phase margin, gain margin, phase margin versus crossover frequency, which I marked as a point. So once I want to change some for the stability analysis, I can able to change this point. So which will be updated in the real time. So all these values you can able to visualize in the real time the poles and zeros in the Nyquist plot or in the Bode plot and the time response. So apart from that, we have the few inductor current and voltage ripples readily available. So for modulation techniques, you can able to understand this part. So if you don't have this basically, if you do some analysis in the AC sweep analysis for frequency response in either in MATLAB or in PSIM, so you can get this particular frequency response directly into the smart control. That option is also available, and if you want, you can directly export this particular results directly into PSIM. So we have the direct option, so where we can interface directly with PSIM also. So apart from that, this is how we can, which I told you earlier. So import frequency response from different softwares like MATLAB, PSIM, Plex, OrCAD, any other. So how we are doing AC sweep analysis, directly you can save the file in the text format and you can able to get back to smart control. Okay, so this is the basic theory of the software. And let me show you the tool. So the GA of the software will be very easy. So here you can see once I open the smart control, so one pop-up window will be opened. So where you can able to design the predefined topology one by one. So according to your requirement, you can able to design that. So we have all the predefined topologies, and if not, you can go with the generic topology, either with the transfer function which you are working, or input frequency response from other text files. So let me show you the basic tool. So I'm just taking a DC-DC converter, single loop voltage mode controlled. Okay, so once I selected that, here we have a single loop DC-DC converter. So in the plant model, we have a different inbuilt models are available, readily models. So like example, buck converter, either with voltage mode or current mode control, like boost, flyback, so forward. So all the converters are available. So for example, I'm just taking a buck converter for a basic thing. So these are the parameters which you have to enter. So for example, I just want to get my output voltage. I'm just assuming some 5 watts or 5 volt output, and I'm just giving required information. So here you can see the plant model. So equivalent plant model of that. So once you selected the parameters, you can press OK. So as I told, this is the workflow. So how you are drawing the flow chart, everything, it will be like that. So once you selected the plant, then you can select the sensors. So as we selected the voltage mode control, we have a different sensors related to the voltage mode control. So that is voltage divider, embedded voltage divider, isolated voltage sensors. So apart from that, recently we have updated the software with equations also. If you are using your transfer function, your own sensor, so you can able to work on that by giving the transfer function of that particular sensor also. So in this case, I'm just taking the embedded voltage divider, or we can able to select the voltage divider. Accordingly, we'll get the gain. So here you can see we took the voltage expected output voltage as 3.3, which is freezing now. So we have to give the reference. Accordingly, it will calculate the gain for the particular voltage divider. And in the compensator, we have the 3 types of compensators. One is type 2, type 3, and PA. Apart from that, if you are using your own compensator, you can work on with your equation part. So for example, right now I'm taking the type 3. So as of now, you have gone with the PA, PID, or some other PD control compensators. So these are the industrial standards, type 3, type 2. So here you can able to see the RAM signal and the equivalent type 3 controller plant model. So once you enter all those values, so now I selected my plant model, sensor model, and the compensator model. So now here you can see the solution map. So in the solution map, you have to set your crossover frequency in the phase margin. So in order to set that, here we have an option called set. So press on set. So this entire white region is just the solution map. So where we'll get the solution. So for example, I'm just placing in my point. I'm just taking my crossover frequency in the phase margin at this particular point for basic reference. I'm pressing OK. Now, once you selected entire equations and points, press on OK over here. So now in this part, you can able to see this is my phase margin, gain margin, and then this is my Nyquist plot, and this is my time response, and these are my inductor voltage versus current time, and this is inductor and diode current time. So apart from that, we have a carrier simulation signals where you are taking the PWM. So now we can tune the parameters. So for example, so in this we have different plant models. So one is this is my control output transfer function, and this green one is my plant transfer function. So this is my control transfer function, and this is my plant transfer function. Plant transfer function. So in this, you can able to see my poles and zeros, which is already available. So now we can tune the parameters. So in order to tune the parameters, we can able to just drag and drag your point. Accordingly, this entire values will vary. So you know the Nyquist stability criteria, the poles and zeros should be inside and out, inside the zero pole. Accordingly, you can able to calculate the stability criteria. If not, you can able to select the minus 3 dB values, and here you can able to calculate the minus 180. So accordingly, you can able to get the entire transfer functions. Now, for example, this is my stable region. So for example, this is my control stable condition. If I want to work, select, import this to PSIM. So just here we have option export to PSIM directly. So I'm just clicking on that. So I'm just I'm just saving that in my desktop as a test file. Test STC, I'm keeping that, and I'm pressing OK. So I'm just exporting all my RLC values which I have given, the initial conditions. Once you selected that, so directly you'll get the output. Okay. So this entire output will get it. So now what I will do is I will show you the schematic result which I have done exported into PSIM. So I didn't do anything in the PSIM part. I just exported the entire smart control results to my PSIM. So here you can see which I selected buck voltage mode control, which I took from the smart control, and this is my type 3 controller, and this is my sensor part. Okay, so everything you got it from the smart control. So for example, still you didn't find the stable region, so you can go back again, and instead of exporting everything, just you can able to export the file parameter itself. So here we have an option file, and just you can click on that. So it will overwrite. So you'll overwrite and you get this output directly. So this is the added advantage in the PSIM smart control and PSIM software. So now I'll show you one basic SSC analysis. So in the PSIM also you can do the SSC analysis. We have SSC probe. So we have SSC parameter block where I can able to enter the start of frequency and end frequency and number of points. So once you selected it, wherever you want, you can just place the SSC probe over here, and you can able to get the results like this. Once you run the simulation, instead of getting the output voltage, directly you'll get this particular sweep analysis. So in this sweep analysis, you can able to get this amplitude and the phase margin. So if you want, you can save this file as a text file. So I'll just show you that. Save as, you can save this file as a text file. So here we have a text file. You can save this file in the text file, and you can able to do this particular, you can import the frequency response from the text file. So you have to select whether it is voltage mode control or current mode control. Once you select it, you can able to select your file part. Text file format you can able to select, and you can do the further analysis in the smart control. So this is how the smart control works. I'm just pressing escape. So any doubts in this particular theory in the smart control? So this is one basic advantage, and someone has asked us this particular interface with MATLAB. So in order to interface with MATLAB, so here we have an option called utilities and sim coupler setup. So first you have to set up this sim coupler with your MATLAB version. So for example, if you are using right now you are using 12.0.3 PSIM version. So in that case, so the MATLAB will be supported 2018 to 2020, any MATLAB version. So first you have to set up the MATLAB setup file. Once you selected that, we have a SIN nodes and SOut nodes. So these are the nodes which is available in the PSIM file. So once you selected this entire circuit, so in this I didn't have any control circuit. I just have this power circuit and a few comparator blocks which I'm using. So now I will design this entire control circuit in my MATLAB. So I'll show you the MATLAB Simulink model which I've designed. So this is my entire control circuit which I've designed in MATLAB. So once you set up the sim coupler model in MATLAB, you'll have this particular block called sim coupler block. Once you selected on that, you have to set your schematic file. So you have to select your PSIM schematic file, which I have done. So you can able to browse it, and you can show schematic also. Once you've selected that, the PSIM schematic will be open. Now, what I will do is I just run the simulation. I'll just run the simulation. I just apply, and I'll just run the simulation for you. So I'm not running any simulation. So you can able to see that I'm just closing this entire windows. So now I have only this file. So here you can see I'm not running any simulation in PSIM. Okay, now I'll run the simulation only in MATLAB. So this is my MATLAB file. So here I'm just clicking on run option. So the simulation started running. So we are doing the code simulation. So one step of PSIM will run and one step of MATLAB is going to run. So, but the results you can able to verify in both PSIM as well as in MATLAB. Okay. So only thing, what are the time step you are giving over here? The times, the same total time should be in simulation control in PSIM also. You should provide the same. So it is 50% done. So we'll wait for a couple of seconds. So here you can see my cursor. I'm not doing anything. I just left it over there. So now the PSIM results will be opened. So how we are getting the SIMView window, the same way directly the PSIM window will be opened. Okay. So here you can see. So I got the PSIM window. This is the SIMView window. So I will say ISP and ISC. I'm just taking, and this is my results. Okay. Now the same results I can able to see in MATLAB also. So the same. This is my 3-phase current. Okay, where I'm keeping the probe over here. So I'm not sure how to track this. No, I don't know. Where is x-axis? So Vinay, where will be the x-axis settings in this?
I think you can click on the waveform itself. No, hand symbol. In that zooming option, hand symbol is there, right? Yeah. It's not coming.
No, it is taking only one cycle.
Sir, just zoom this out.
Which one? No, I want to set from 0 to 0.5.
Go to the
so
tools, I think. Tools. Can you go to the tools? Axis scaling. X-axis unit limits down. Yeah.
Scale X and Y axis limits. Okay. I'm not getting any window.
Okay.
This I'm not sure. So basically here it is taking 0.4912 to 0.5. So the same results I'll show you over here also. So here you can see the same results. The same results will be available over in MATLAB also. So whatever the results you have seen in PSIM, the same results you can able to see in this particular results. So this is how the simulation will work. This is called co-simulation. So like this, you can able to co-simulate with MATLAB as well as PSIM. So any other queries from your end?
Yes, sir. Hello, sir.
Yes, tell me, sir.
So regarding this student point of view, what are the things that we are going to concentrate? Because you are showing so many options, we may be in confusion, but actually, what exactly the options we can practice so that we will be acquainted with this.
Students, yeah, for students, what we can tell was, so we have here help option. So tutorials. So we have all the tutorials how to do the STC analysis for switch mode controls. So the hybrid electric vehicle design. Someone want to design hybrid electric vehicles.
Okay, sir.
So we have the hybrid vehicle design suits. So they can able to refer all these documents for basic understanding. And we have video tutorials. So we have 100+ video tutorials getting started with PSIM. So how to design a simple buck converter. So how to analyze waveforms in SimView. So which we have done today. So how we are analyzing and how we are doing buck converter and how to perform AC sweep analysis. So introduction to thermal model. So and C code simulation. So these all things will be helpful.
Sir, thank you, sir.
Yes, hello. Can you hear me now? Okay. So Vinay, so anything you want to present for them?
Yeah, as of now, no. But powerful, what we can do.
Yeah. So just show them the overview of PowerForge.
Okay.
Maybe I can give the access. So we'll show you the overview of PowerForge also right now. So maybe for reference, you can take this part. So if someone want to, so here we have the basic examples. So in the demo version also, you can able to work on that. Open examples. You can click on the open examples and you can work on that. So if any queries is there, please let us know. We will help you out. Yes, Vinay, you can start with PowerForge.
Yes. So yeah.
I think this presentation will be fine. No need of the software.
Okay, fine. Yeah. So this is another one software we have. This is actually web-based software. It doesn't require to download and all. So it is actually for a converter design, like a DC to DC converters and DC to three-phase AC converter design, and the cost estimation and break to find the breakdown values like mass, volume, and power density. So these all estimation things we can do here. So yeah, and this actually found in 2016 and in France, and here it got so many innovation awards also. So here you can see the design topologies are like these are the power converter challenges, right? Like which topology we need to use and which magnetics means which come under inductor and capacitor means circuits. So and thermal management means the heat, how to extract the heat from the switches, and the command means which type of switching technology we need to use. These all the power converter design challenges nowadays. So yeah, in the left hand side you can see this is a traditional way where you can enter the specification from the user, and you can prepare the Excel sheet. From again you are going to the data sheet and manual calculation. After the calculation, simulation, and again we are changing the values, and again the same process will repeat so many times, and finally we will get the filter design values. Again we need to design the filter and what is the filter cost, everything we need to study. So this will be like a very big process. But in the when you give the specifications directly, it will take elements from the library, and we can do so many iterations in one, just like in a minutes, so that you can get is the most efficient design that you can select, and from that design you can use the design in a same PSIM software also. You can import to the design PSIM software, and you can download the report also. That is possibilities are there. So this is the present actually DC to DC converter and DC to three-phase AC converter. So these two type of converter technologies are available, and automated design generation from two-level to multi-level inverter also we can do this. And broad libraries, devices, and elements are materials are available, and you can ready to use file exports for the industry standard software. Means like you can download in the PSIM software. You can export to the PSIM software, or else you can download in the PDF format. You can download in the Excel sheet. So this all design downloads. So we can do. And this, as I said earlier, this is a cloud access. Don't need to require any software download under. Just wherever you go, you can use that software. So this is the one phase where we can design the 3-phase DC to 3-phase AC. So this is a line diagram like DC differential mode filter, AC differential mode filter, macro cells, cooling, and switches controller. So this particular these are the elements will be there. So we need to give inputs for the DC differential mode filter and AC differential mode filter, cooling, and macro cells and switch controller. So when you give these inputs, required inputs, so you will get in this way, like see here I am used different sign PWM technique, sign PWM here, SP PWM with the different frequencies, okay, and different switches. Here IGBTs I used, here MOSFETs. So different switches, different frequency, different topology I'm used, and I'm seeing that how the output is varying and efficiency is varying, power loss, cost. So everything I can estimate here. Even cost means we will give the sample cost values. So according to that, it will come fully. It will find the what is the maximum cost it can be. So after that, you can compare all the different type of topologies. Here you can see this is different type of topology. This is different type of flying capacitor with the, this is without flying capacitor for the inverter technology. So this is the output how it is varying for the efficiency versus power density versus so number of levels. So how it is changing the output values. So this way you can construct your own waveform, or sorry, your own plots, or else you can, there will be a maximum, it will give all the plots. If you want any plot also you can create, and you can get the breakdown plots like for example like mass coming to the mass, how much it will require the AC differential mode filter, cooling, how much it will require, and DC differential mode filter, how much it will require, macro cells, how much it will require. Like that, it will give all the breakdown values for these things like a mass, volume, power loss, efficiency, cost. Okay. And finally, we can export to the PSIM, we can export the flex, we can export to the them to use this design, and we can download the Excel report, or as efficiency versus power data also we can download. So these are the advantages, like a software access from anywhere, because it's a software based, means web based, and very easy to work. And this is mainly for the power converter design only and comparison. Okay, we can do multi-sweep analysis for the switching frequency and semiconductor switching topology. Means these all for these all we can do the sweep analysis, and also multi-user can be calculated in the single plane. So yeah. So okay, this is what the PowerPoint software. Just want to give you the overview. Okay, now if you have any queries, you can ask. And thank you for your attention.
Thanks, Sunny.
Yeah, thank you.
So if you have any queries, you can ask us. So we'll be there for the next 5 minutes. So 12 o'clock, you can close the session. So tomorrow's session will be on electromagnetics, where they use the JMAX software, how to design the electrical machines, either induction machines or PMSM machines. So it will be purely related to your electric vehicles. So any machine, how to design, they will show you. So basically we'll do in AutoCAD or any ANSYS software. So for electrical modeling part, this software will be very helpful. So how to use the lap winding, wave winding. So you all studied the electrical machines, right? So this the same way they will going to show you in the practical way. So practical manner, how they will design that. So kindly fill up your feedback forms and send to the respective team. So they will work on that, and we're going to share the presentation as well as the schematic files, what we have done today, and the recording of the sessions.
Dear participants, please fill the feedback form. Dear participants, please fill the feedback form. Vinay sir?
Yes, yes.
Sir, please keep within 2 minutes, sir.
Yeah, yeah, sure.
Close the session after 2 minutes.
Okay,
Yeah,
fine.
we will close by 7:58.
Okay, okay, sir. Okay, sir. Please stop the recording, sir.
Yes, yes.